All right, everybody. In this video, we'll be looking at how we can classify um, singularities for complex functions. And so we're going to look at the zeros and what are called the poles of a complex function. So suppose, let's say a point z equals z naught is an isolated singularity, right? Of a analytic function f of z, okay? So that means, f of z is represented as a Laurent series. Laurent series is a sum of a collection of terms that include, I'll say the negative coefficients, right? Z minus z naught to the minus k, should be minus k here, minus k, plus the sum of the positive terms to the k power. This part of a Laurent series, so this here is a Laurent series. Maybe I should label this a little bit clearer. So this whole thing is what's called a Laurent series, right? The terms with the negative coefficients here, that will indicate what's called the principal part, right? The principal part. And the terms that have the positive coefficients, this is what's called the analytic portion, analytic part, right, of a Laurent series, okay? So, and so this series is valid on a puncher disk, right? It's an open disk that does not contain the center, right? So it's a disk that does not contain the center, so that means this has to be strictly positive, right? Um, so what we're going to do is we're going to classify the zero or zeros, zero or zeros of a function by counting the number of terms in the principal part of the Laurent series. Okay? We have the Laurent series. Okay? That's essentially what we're doing here. So we're going to look at the principal part of the Laurent series, and we're going to classify what type of zero it is for a particular analytic function. Okay? So so right away, we're going to look at the classification of zeros of f of z. Okay. And then in this example, we're going to assume that f of z is analytic along a isolated singularity z equals z naught. Okay. All right. Oops. So the first type of classification is what's called a removable singularity. Okay, removable singularity. So this is a type of zero where you have no negative coefficients, right? So this is a type of singularity where its Laurent series has all coefficients a to the minus a sub minus k are equal to zero, right? So all of them are equal to zero. So you'll essentially have just the analytic portion only, right? Um, um, z minus z0 plus a2 times z minus z2 squared and so on, right? So that's the first type of classification. The other type of classification is what's called a pole, right? A pole. Um, so if we can express a function as a finite number of terms in the finite amount of negative terms, so z minus z naught to the minus n plus a to the minus n minus 1 z minus z naught raised to the minus n minus 1 divided by z minus z naught plus a0 plus a1 times z minus z naught plus a2 times z minus z naught squared, right? That pattern keeps going. But the most important part is that if the analytic portion has a finite number of terms in that sum, then we'll say z equals z naught is a pole of order n. Okay. Um, uh, oh, and there's a special name if the n value equals 1, right? So if the n equals 1, then z equals z naught is a simple pole. That's what's called a simple pole. All right. Um, and there's also what is called an essential singularity. Okay. And basically what that means is you have an infinite collection of the negative coefficients, right? So your Laurent series will look something like this. You have an infinite amount of negative terms in the Laurent series. Z minus z naught squared plus a to the minus 1. And then you'll have an infinite number of terms for the analytic portion. Okay. So this is what's called an essential singularity. Okay. So um, uh, those are the different classifications of the zeros of complex functions, right? And it all has to do with the how we express its Laurent series. Okay. So let's look at some examples here. Um, Okay. So let's say in these two examples, we want to show that f of z, these functions they have a removable singularity at z equals 0, right? So here's the first one. F of z equals e to the 2z minus 1 over z. Now, the good indication here is to look at the Maclaurin series for e to the z, I'll say, right? We looked at last time what the Maclaurin series of e to the z looks like, right? So it's 1 plus z squared over 2 factorial plus z cubed over 3 factorial, and this pattern keeps going, right? So this is the Maclaurin series for e to the z. And so if I want to figure out a series expansion for e to the 2z, well, just plug in 2z to each z term in the sum, in the previous sum, right? So it's just 1 plus 2z plus 2z squared over, 2 factorial plus 2z cubed over 3 factorial plus, this pattern keeps going, right? And so this equals 1 plus 2z plus 2 squared z squared over 2 factorial plus 2 cubed z cubed over 3 factorial plus that keeps going. And so e to the 2z minus 1, well, this is essentially equals to this sum that we found, right? So equals to the sum that we found. Minus 1, right? The ones will cancel here. And so you'll have 2z plus 2 squared z squared over 2 factorial, right? Plus 2 cubed z cubed 3 factorial plus this keeps going, right? And so therefore, e to the 2z minus 1 over z, well, this equals to 2 plus 2 squared times 2 factorial times z plus 2 cubed over 3 factorial times z squared plus, and this pattern keeps going, right? So notice here, there is no negative z terms, right? No negative z terms. So what that means is that z equals 0 is, in fact, a removable singularity, right? A removable singularity. Okay. Right. So this was f of z. Okay. So f of 0, well, all the terms that have z's in it will become 0, except for the constant of 2. So f of 0 would be 2 in this case. All right. So f of 0 would be 2. And that's another way to define an analytic function at that function. So if you have a good grasp of that example, I want you to try to work this one on your own. Show that z equals 0 is a removable singularity for this function. Divided by z squared. Okay, so once again, we have to show, or you have to show, that z equals 0 is a removable singularity, okay? So pause the video and I want you to work on this example on your own. Okay, so I assumed you worked on this example. Let's work out, see what we get. So we need to recall the Maclaurin series for sine of z, right? Z minus z cubed over 3 factorial plus z to the 5th over 5 factorial right? Minus z to the 7th over 7 factorial plus, right? This pattern keeps going, right? So sine of 4z, all we have to do is just plug in 4z for each z term in the Maclaurin series, right? So we'll have 4z. So we'll have 4z minus 4z cubed over 3 factorial plus 4z to the 5th over 5 factorial minus 4z to the 7th over 7 factorial plus, and this keeps going, right? And so this equals to 4z minus 4 cubed z cubed over 3 factorial plus 4 to the 5th z to the 5th divided by 5 factorial minus 4 to the 7th z to the 7th over 7 factorial plus yada, yada, yada. Okay, so sine of 4z minus 4z, well, if we subtract this sum by 4z, what happens is, well, the 4z's will cancel, right? And so what that will leave us with is the 4z canceling, and we'll have a minus 4 cubed over 3 factorial times z cubed plus 4 to the 5th shoot 4 to the 5th over 5 factorial times that z to the 5th z to the 5th power minus 4 to the 7th over 7 factorial times z to the 7th plus, and this keeps going. And so sine of 4z minus 4z divided by z. In terms of a Laurent series, this equals to minus 4 cubed over 3 factorial times z plus 4 to the 5th over 5 factorial times z. So it's z squared. Okay. Yeah, z squared. I'm sorry. So that's z cubed minus 4 to the 7th over 7 factorial times z to the 5th plus, and this keeps going, right? So this right here is f of z, right? And so f of 0, well, that would be 0, okay? And so that function would be analytic at that point. All right? That's how you figure out the removable singularity at that point. Okay, so I want to mention a couple of I'm going to show you a couple ways to show if a function has a 0 of order n or a pole of order n. Okay, so here's a couple of theorems for you to write down. So a function f of z is analytic on a open disk and has a 0 of order n if and only if, I should write out, if and only if f of z can be expressed as z minus z naught to the n times phi of z. Okay. Where phi of z is analytic at z equals z naught, and phi of Z naught is not zero. Okay. All right. So, and also, I'm also going to write out another important fact. Okay. Let me put this here. So a function f of z is analytic as a pole of order n if and only if f of z is equal to phi of z divided by z minus z naught to the n power. Where phi of z, excuse me, is analytic at z equals z naught and phi of z naught is not zero. Okay, so let's go over these again. So a function f of z is analytic. And then if you have an analytic function and it has a zero of order n, you can express f of z as a factor, right? Z minus z naught to the n times an analytic function phi of z, right? Phi of z is analytic and phi of z naught is not zero, right? So that's important. You can factor out z minus z naught to the n, okay? Likewise, if we have a function that has a pole of order n, we can express the same result, right? We can express f of z as an analytic function phi of z divided by z minus z naught to the n power, okay? Where phi of z is analytic at z equals z naught and phi of z naught is not zero, okay? So those are important. So let's go over some examples on how to better classify zeros and poles of complex functions, right? So determine the zeros and their orders for the following functions. So I have f of z equals to z to the fourth plus z squared. And then this one. So I want you to pause the video and I want you to work on these couple problems here. All right. So you want to determine the zeros of these following functions and try to figure out the order of each of those zeros. Okay. Oh, one more thing. Here's another one that I want you to think about as well. So this one here. Sine squared of z. That's a good one. All right. So I want you to think about these examples and try and see what you come up with in your final answer. So yeah, good luck with these. Okay, so I assumed you worked on these problems. Let's go over them one at a time. So let me move this out of the way. We'll go over this later. Uh, so part A, we want to look at how to classify the zeros and their orders. Okay. So right away, we can factor a z squared to each term. So we'll have a z squared times z squared plus 1, right? So here, we can use difference of squares, right? So we can factor that term again. So we'll have a z squared here, and then times z plus I, and then z minus I, right? I squared is -1, right? So you can express z squared plus 1 as z minus I times z plus I, okay? So we want to look at where this function is 0. Excuse me, z plus I and z minus I, right? Well, we have a 0 where z is 0, right? And we also have a 0 at z equals I, and then z equals -I, right? So it's similar to looking at what is the zeros and the multiplicity of a function, right? In algebra, right? It's the same exact principle. It's the same exact concept, right? Right. We have a 0 at z equals 0 with multiplicity 2. So it has an order of 2. Okay. Z equals I is a 0 of order 1. And also z equals minus I with an order of 1 as well, right? It occurs once. Okay. All right. Classifying what zeros for f of z are and their order, right? It's similar to looking at the different zeros and their multiplicity in algebra, right? So the exact same concept, right? So that's how you figure out part A. That was pretty straightforward. So part B, we want to look at classifying the zeros and the order for where is it? This function here. So f of z equals e to the 2z minus e to the z, right? So again, we can express we can factor out an e to the z, right, to each of those terms. So I have e to the z minus 1, right? So so we'll have 0 equals e to the z times e to the z minus 1. Okay. So the only possibility is that e to the z is 0 and e to the z minus 1 is 0, right? This is always non-zero, right? So this is always non-zero. So that is clearly false. So what is leading us to conclude is that e to the z has to equal 1, right? Okay. So what that means is z would equal to the natural log of 1 plus 0i, right? 1 plus 0i. Okay. So, all right, so this would equal to log base e of 1 plus I times the principal argument, right, of 1 plus 0i, which will be here. But the roots for z, right, remember the argument is this can take on multiple values, right? So when theta is 0, we'll have 1 plus 0i, right? If theta was 2 pi, well, I guess, let me start over. So when theta is 0, we're at 2 pi. right? If we rotate 2 pi radians clockwise, we'll also get an angle of 0, right? Um, so yeah, so this is I times 0 here, I times 0, right? But also if we rotate 4 pi, right, radians clockwise, we'll also get 0, right? And also it will work for the counterclockwise direction. So if we go counterclockwise, or I should say clockwise, um, 2 pi radians will still get 0. And then minus 4 pi radians will get 0 rate. We'll get an angle of 0, right? 0 radians. Okay. So the okay, so this would be 0 plus I times 2 pi n, right? Where n is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, and so on, right? Okay. So, okay. And so each of these would be a 0 for different values of n. So each z value, each z value is a 0 of order 1. Okay. Since we have a 0 and then plus or minus 1 and then a plus or minus 2, right? So these are unique values of n that will give you the 0 at 1 plus 0 I. Essentially what that means. Okay. So hopefully that makes sense. The last example is going to be the same format as in part B. So we know that sine squared of z, right? So we know that sine of z equals 0, where z is equal to, well, so sine is 0 at, well, z equals 1 plus 0 I, and then minus 1 plus 0 I, right? I'll say that. Okay. But right, so these numbers in terms of the polar form, so yeah, so okay, so in polar form, so when we have points at, so when we have points on the positive and the minus real axis, that's where sine is 0. Okay. So basically, where z is equal to um, where so okay. Or maybe I can express yeah, that will probably help if I sine of x hyperbolic cosine y minus I believe it's cosine y times hyperbolic cosine of x. Yeah. Yeah. I'm forgetting the formula, but um yeah, so really what we can do is we know that sine of z is 0 um where we have an integer multiple of pi, right? That as its uh argument, right? So this is where z is equal to 2m pi. Yeah, so 2m pi, 2m pi I. So this is of order 2. Order 2. Okay. So 2 pi I of 2m pi I of order 2, and n is a positive integer, right? So sine of pi is 0, and then sine of 2 pi is 0, right? So um yeah, so oh, I'm sorry. So okay, yeah. So sine, yeah, so sine of z is yeah, so it's sine of x hyperbolic sine y and cosine x hyperbolic. Is it sine y? Yeah, hyperbolic sine y. Okay, I'm forgetting the formula. So um yeah, you can break down sine of z in terms of the real and imaginary components, and this is what it should roughly look like, right? Um yeah, oh, it's a hyperbolic cosine. Okay, yeah, I get it. Hyperbolic cosine. And then so cosine x hyperbolic sine y. Okay. Yeah, all right, that's right. So that's sine of z, right? So sine of z, so that's where it's equal to 0 plus 0 I, right? So um and z would be 2m pi. There we go. That's it. So of order 2. So it should be z equals 2m pi. And then n is just a positive integer. N is any integer, right? N is 0 plus or minus 1 plus or minus 2 plus or minus 3. And all of these different n values, since we have an exponent of 2 here, that would give us each 0 in order of 2. Okay. So hopefully that made sense. Okay. Um, the last examples determines the different poles and their orders of complex functions. So let's go over those now. Okay, so determine the order of poles of f of z equals 1 plus 4i divided by z plus 2 times z plus I to the fourth. And this one, f of z equals tangent of z. And this one, okay. So for these examples, you want to determine the order of the poles and what poles are there in these three functions. F of z is equal to 1 plus 4i divided by z plus 2 times z plus I to the fourth. Part B is f of z equals tangent of z, and part C equals to 1 over 1 plus e to the z. Okay, so I want you to pause the video and I want you to work on these examples. Okay, I assumed you worked on these problems. Let's go over it. Okay, so the way to determine the poles, what poles are there, and their respective orders. Well, just look at so for one thing, just look at if it's a rational function. So typically it's going to be a rational function, right? And then just look at where the denominator would be zero, right? So we will have, so in this case, we'll have poles at z equals -2, right? And then z equals -I, right? So z equals -2 is a simple pole, right? It occurs once, right? The exponent here is 1, right? The exponent for the other 0 is 4. So what that means is, the heck just happened? So what that means is z equals minus I is a pole of order 4, right? And then you can check for yourself that f of z is equal to z minus z plus I to the fourth times, right? You can express this function as 1 plus 4i over z plus 2. This is your phi of z, right? Right, minus I plus 2. 2 minus I is not 0, right? So, and it's also analytic, okay? So it's analytic at z equals minus I, right? So z equals minus I is a pole of order 4. All right, so tangent of z, part B. So f of z, by definition, is equal to sine of z divided by cosine of z, right? That's tangent of z, okay? The poles is where the denominator is 0, right? So what that means is we want to figure out the values for z, for which cosine of z is 0, right? Cosine of z is 0. Um, so uh, according to the complex definition of uh, cosine of z, so uh, okay, so okay. I don't think I need it, but so cosine of z, this is where it's 0. Um, right, so e to the over 2. Right, and so if z is equal to x plus iy, I think it would be helpful if you wrote out cosine of z in terms of the real and imaginary components. So yeah, so cosine x hyperbolic cosine y minus I times hyperbolic rate sine of x times hyperbolic sine y, right? Okay, so what we want to do is so we have to look at where cosine of z is 0, right? So cosine of z is 0 where it's at pi over 2 and then 3 pi over 2, right? Usually, right? So really so I guess another way to express this yeah, I don't want to use the cosine z definition. I think it's pretty straightforward just to look at where cosine is 0. So z has to equal to it's an even integer multiple of pi. So really it's just 2n plus 1 times pi over 2, I meant. Okay, so pi over 2. And then n is a integer, right? So tangent of z is not raised by an exponent, okay? So so um so each z value is a simple pole. Okay, is a simple pole. All right. Cosine z is 0. Okay. Yes. Okay. So all right. So that would be the zeros for that function. That would be the poles for that function, right? And then part C, we have f of z equals to 1 over 1 plus e to the z. We want to look at the poles for f of z. So basically looking at where the denominator is 0. Okay. So what that means is 1 plus e to the z has to be 0, or what that means is e to the z is equal to -1. Okay. So e to the x, e to the iy has to equal to -1. If z equals to a real and imaginary component, x plus iy. So we'll have e to the x times cosine y plus I times sine y equals to -1, right? So e to the x cosine y equals to -1, right? And then e to the x times sine y has to be 0. Okay. Well, e to the x is not 0, right? So what that means is that sine of y has to be 0. But we know that sine of y is 0 on the x-axis, on the real axis, right? Sine of y is 0 on the real axis. But what really comes into play is this value here, right? So we also know that cosine of y is equal to -1 on the negative real axis, right? So that means is that y has to equal to an odd integer multiple of pi. Okay. So what that means is that z is equal to 2n, not over 2. I meant an odd integer multiple of pi. So really, let me erase that. And I want to rewrite it like this times I. Okay. And then each of these zeros, so if you notice, 1 plus e to the z is not raised by an exponent, it's raised by 1, right? So each of the zeros, so each z value is a simple pole. So it's a pole of order 1. Okay. All right. So hopefully that made sense. Um, and then yeah, that's basically most of the problems you'll work with, right? If you have a Laurent series, if so, oops, so really to determine the classification of zeros in a of a complex function, all you have to do is look at the number of negative terms in the Laurent series, right? Okay, so um, and oh, okay, my screen's not working. And if you have an infinite number of terms in the principal portion of the Laurent series, right? Um, that will give you what's called an essential singularity, right? So I was going to write down another example, but my screen's not working for some reason. Okay. Okay, let me do this here. Ah, there we go. Okay. So if I go back here, so that's the theorem to determine the poles and zeros of an or and their orders. If you have a essential singularity, right, you'll have an infinite number of terms in the principal portion of the Laurent series, right? It doesn't matter about the analytic portion, it matters about the principal portion. So as an example, show f of z equals to, so I have z cubed times sine of 1 over z has an essential singularity at z equals 0, right? And the idea is to look at the Maclaurin series, the Maclaurin series of sine of z, right? You just build off from that. You should get an infinite term of negative z terms, right? Negative z terms, I mean negative exponents on z. Okay. And then just to end it off, I want you to work on these problems if you choose to do so, right? you can't get better at this math just by listening to me throughout the whole time. So try to challenge yourself to work on these problems that I list out. So if you have questions, always reach out to me. Okay. 24, 28, and then 30. That should be good. All right. So for next time, we're going to look at an important theorem in complex analysis called the residue theorem. Okay. And it looks at different zeros and poles. And I should point out that the coefficient in the Laurent series, a to the minus 1, this is what's called the residue. So we'll go over more stuff on Laurent series and how we can use the residue theorem to figure out I guess integrals of different contours, right? That's what the residue theorem is about. So with all that presented, I hope this was helpful. If you have questions, just let me know in the comments, or just shoot out an email. Okay. The email is in the homepage on my YouTube channel. So I hope this is going well, and I will see you all next time.